Coker operations are quite complicated. Operators must pay attention to many issues ranging from feed quality in terms of sludge content and high asphaltene concentration, mitigating coker fouling and corrosion, product quality, wastewater discharge, and so on. In this seminar, we focus on a common, well-known problem: coke drum foaming. Coker operation can be quite complicated. Operators must pay attention to many issues ranging from feed quality in terms of sludge content and high asphaltene concentration, mitigating coker fouling and corrosion, product quality, wastewater discharge, and so on. In this seminar, we will focus on a common, well-known problem: coke drum foaming. Foaming in the coke drum typically leads to coke carryover in the vapor lines and in the main fractionator. Excessive carryover, however, will negatively impact the heater charge tubes, the overhead vapor lines, the fractionator, the heater charge pump, and the blowdown system. Foaming problems in coke drums most commonly occur after drum switching, either in the drum that was just filled, or in a drum that is being filled. Poor coke drum level monitoring can also result in foam carryover during filling. Fortunately, the majority of foaming issues are the result of identifiable operating problems and/or operator errors and can be rectified. Following a drum switch, a pressure drop of 1 to 2 psi or 6.89 to 13.78 kilopascals every 5 minutes is desired. To suppress foam carryover, it is recommended that the coke drum operator maintain an ascending pressure on the top of the full coke drum for a period of 15 minutes. Full coke drums are also susceptible to excessive foaming during the steaming process. Pinching the vapor valve will help to maintain pressure in the drum. Furthermore, it is recommended not to allow the overhead temperature to drop below 780 degrees Fahrenheit or 415 degrees Celsius. Foaming can happen during the coke drum changeover period, during post-changeover steaming towards fractionators, or while steaming the drum towards blowdown system. Pressure drop is considered the greatest contributor to foaming issues, and there are several flaws that can lead to excessive pressure drop and eventual foaming. During the 2011 National Petrochemical and Refiners Association Q&A session, a representative from Indian Oil Corporation shared operational experiences to deal with foaming during coke drum changeover. These operational experiences include changeovers taking 30 minutes to carry out, achieving an operating temperature of 260 to 280 degrees Celsius or 500 to 536 degrees Fahrenheit for 24-hour cycles, and around 300 degrees Celsius or 572 degrees Fahrenheit during 18-hour cycles, increasing size of condensate outlet line from 6 to 14 inches, carefully monitoring condensate draining to ensure no condensate goes with steam during steaming, beginning antifoam injection 4 hours prior to drum switching, and increasing the wet gas compressor suction pressure set point should higher than normal pressure drops occur. Beyond the previously mentioned operational practices to maintain pressure in the coke drum, antifoam agents are used in cokers to prevent the buildup of foam. Silicone addition has proven to be an effective method to suppress foaming in delayed coker drums. The primary antifoams used in cokers are 60,000, 100,000, and 600,000 centi-Stokes or 0.06, 0.1, and 0.6 square meters per second polydimethylsiloxane. A common problem with silicone antifoams, however, is entrainment in the overhead gas stream. One strategy to enhance the impact of antifoam additives is to double the dosage immediately following drum switch while the pressure pinch is being applied, and to return the dosage to normal after the pressure in the drum is stabilized. Refiners can also reduce the amount of antifoam agent by selectively adding the agent within a predetermined time window before a drum switch or when the top-level probe detects a reading. The injection may be automated to react to the level probe alert. The use of a carrier stream such as heavy coker gas oil or light coker gas oil in overhead gas stream would prevent silicone antifoam entrainment. The dilution of the silicone with a carrier oil to allow good dispersion of antifoam can be performed using a batch procedure with a day tank containing an impeller or air sparge, which is recommended by Citgo Refining and Chemicals, or an automated inline injection system that creates a diluted mixture that is sent into the drum, which is recommended by Turner, Mason and Company. Another way to avoid antifoam entrainment is to maximize the distance between the injection nozzle and the vapor outlets so that it is no closer than 0.5 to 1 meters or 1.6 to 3.3 feet from drum walls. According to Baker Petrolite, switching to a higher centi-stoke antifoam lowered the silicone concentration in heavy cracked naphtha, light coker gas oil, and heavy coker gas oil products. To make sure that too much antifoam does not reach the fractionator, ASTM D7757, test method for silicon in gasoline and related products by monochromatic wavelength dispersive X-ray fluorescence spectrometry can measure silicon and thus antifoam in naphtha, gasoline, refinery fuel gas, ethanol, ethanol fuel blends, and toluene. Here is our sponsor's experience. Refinery hydrotreating units use expensive hydrodesulfurization or HDS catalysts that can be easily deactivated by silicon, but the antifoams used in delayed coking operations are typically silicon-based. The challenge is to control foam in the coker, prevent silicon contamination in the hydrotreater, and still run an efficient and profitable operation. Specifically designed to reduce silicon contamination, patented FoamStop Low Catalyst Impact or LCI antifoam controls coke drum foaming while reducing HDS catalyst deactivation. FoamStop LCI antifoam helps you control coke drum foam and lowers silicon concentrations in coker distillate streams, minimize the cost and frequency of downstream hydrotreater catalyst replacements and improve refinery profitability. FoamStop LCI antifoam quickly knocks down foam in the drum when the silicone oil is first injected and controls foam buildup during and after a drum switch. This innovative coker LCI antifoam protects your equipment and helps maintain efficient, problem-free operations. FoamStop LCI antifoam is more thermally stable than traditional antifoams, making it more effective at lower silicone dosages in the coke drum. The decreased silicone requirement reduces the level of silicon in coker distillates, slowing catalyst deactivation rates, and increasing hydrotreater catalyst life. A refiner was treating their coker with an antifoam that was contributing 3,500 pounds of silicon per year carryover to downstream units. The refiner was experiencing an increase in the silicon content of incoming crudes, resulting in rapid contamination of their downstream catalysts. In an effort to address this issue, Baker Hughes GE recommended the FoamStop Low Catalyst Impact or LCI antifoam to address the problem. The FoamStop antifoam was trialed over 32 coke drum cycles to compare to a previous run of 32 cycles using the incumbent antifoam. Fresh feed and furnace charge rates were similar for each case. The trial run had a slightly higher charge rate, 21.3 thousand barrels per day over 19.8 thousand barrels per day, which contributed to a slightly reduced cycle time of the coker. The amount of silicon added to the drum by the antifoam was reduced by 68%, from 0.95 pounds of silicon per thousand barrels per day to 0.30 pounds of silicon per thousand barrels per day. Samples of coker naphtha were taken during the drum cycle for the base case and the trial case. When using the incumbent antifoam, the silicon concentration in the naphtha samples was 19 parts per million of silicon. When using the FoamStop antifoam, the silicon concentration was 6 parts per million, confirming that the contamination of coker naphtha with silicon was lower when using FoamStop LCI antifoam. Overall, it was estimated that FoamStop LCI antifoam decreased the amount of silicon entering the naphtha stream by 2,700 pounds per year, a reduction of 78%. This extended the catalyst's life by an estimated 81 days.